in Antarctica. The difference in temperature between those hottest places on Earth is about 80 or 90 degrees Kelvin. On this hot Jupiter exoplanet, from the Kepler data, the difference in temperature is more like well over 1,000 degrees Kelvin, and possibly even more. So this planet is not like anything in our solar system. And now I'm going to go into a bit of technical detail about what is going on here. We can think of a planet atmosphere in different layers. And in each layer, there's a competition between what happens to the energy that the planet absorbs from the star. First of all, HAT P7b is orbiting a huge amount of energy from the star. It's absorbing a huge amount of energy from the star. And this energy can either be absorbed to heat one side of the planet and re-radiated back out instantly, or the energy can be absorbed by the planet and circulated all around so that the planet has more even temperature all around, more like the planets in the solar system. And which physical mechanism wins this competition depends on how far in the atmosphere the radiation from the star can go. So if the radiation from the star gets absorbed in a very, very high layer in the atmosphere, then the radiation will heat the star and be emitted back out immediately. And one side of the planet will be hot, the other side of the planet can't be heated at all. If, on the other hand, that energy from the star goes really deep into the planet, very deep in the atmosphere, then the energy is most likely to be circulated around the planet, moved around the planet in a very complicated atmospheric circulation with possibly very high winds. And then the planet will be about the same temperature all around. So what the light curve is telling us is that there must be a huge absorbing layer very high in the planet atmosphere. Think of it kind of like a gigantic ozone layer. Only this planet wouldn't have ozone. It's too hot and doesn't have the right kind of chemicals. We think the absorbing particles could be a number of things. It could be titanium oxide or vanadium oxide. Those aren't things we hear about very often, but in astronomy, in low-mass stars, they're quite common. They have strong absorption features all across the visible wavelengths. Or perhaps it could be hazes. Other people have discussed hazes, such as sulfur allotropes, that are forming from UV radiation from the star, which splits up some molecules and makes haze. And that also could be playing a big role in absorbing a lot of this energy very high in the atmosphere. Now, we've seen phase curves before in the infrared with the Spitzer Space Telescope, and the Corot telescope has seen one approximate phase curve at similar wavelengths to Kepler. But I just want to say why I'm so excited about the Kepler data, because what we're seeing here is data of HAT P7b taken over 10 days only. With Kepler, we will have data taken over hundreds of orbits, up to about 500, well over 500 orbits of this one planet. So there's a lot we can learn by studying this phase curve in a lot of detail. And myself and other Kepler team members are working on this data. We're using complementary data from other telescopes like the Spitzer Space Telescope to try to put together more of a story of what's going on in this atmosphere. And I just want to finish by saying this exquisite data that we're seeing today is just the tip of the iceberg. We're really looking forward to everything that's going to come with Kepler. We see a kind of world of exoplanet exploration where discoveries will come much more rapidly than they have in the last 10 years, and that has even seemed really rapid in the last 10 years. And now I'm going to turn it over to Alan Boss, who's going to tell us about what some of those discoveries might bring for us. Alan.
Thank you, Sarah. While Kepler's discovery of the optical light from this hot Jupiter HAT P7b is stunning indeed, the real implication of this, though, is, as Bill pointed out, that this means that Kepler does indeed have the ability to detect the transit of an Earth-sized planet passing in front of a Sun-type star, producing a very tiny dimming. And now we know for sure that Kepler can actually measure that. That is, after all, Kepler's primary mission. Kepler is being launched not just to find hot Jupiters, that's sort of a secondary product, but its prime mission is to count how many Earths there are around Sun-like stars in our region of the galaxy. We now know that Kepler can do it. But the question that remains is, how many Earths are actually out there for Kepler to find? Can I have the first image, please? So what's shown here is the discovery space for extrasolar planets. It shows roughly 350 or so planets that have been found so far by other methods by astronomers, primarily around Sun-like stars, more or less same mass as the Sun, some lower mass stars as well. What's plotted is the mass of the planet, units of the Earth's masses vertically, and horizontally the distance of the planets from the stars, or units of the Earth-Sun distance, which is 93 million miles, also known as 1 astronomical unit. And so the yellowish, orangish dots are the planets. You can see HAT P7b rather is located on the left-hand side. It's very close to its star. That's why it's so hot. And there are a lot of other hot Jupiters that are known. Kepler will find a lot of those. Farther out, there are lots of other Jupiter-sized planets, maybe several hundred times the mass of the Earth, up to thousands times the mass of the Earth. These are what we would call cool Jupiters, or perhaps not as cold as Jupiter, but they're probably very much analogous to our own gas giants, Jupiter and Saturn in our solar system. More intriguingly, they have recently found, in the last few years, objects with masses down as low as the masses of Uranus and Neptune, sort of in the range of 5, 10, 15 Earth masses. And the ones that are farther out are the so-called cold super-Earths. We believe they probably really are ice giants like Uranus and Neptune, which have migrated in perhaps a little bit. But even more intriguingly, farther in yet, are objects on the lower left-hand side of the plot, which we call hot super-Earths. They're much like the hot Jupiters, since they're so close to their star. It's just that their masses are much more similar to that of the Earth. And based on formation models and the geometry of those solar systems, we believe those objects actually are very much analogous to the terrestrial planets of our solar system. They really are just oversized Venuses and Earths, Mercuries and Mars. You notice that so far, no one has found any planet right within the habitable zone. That's the green area delineated on that plot. And what Kepler is going to do for us is basically fill in. It's going to fill in some high mass objects as well, but in particular, the really novel thing Kepler will do is fill in the bottom half of this plot. And in particular, we'll start populating that green area, the green area where we believe that planets, if they have water on it, the water could be liquid, and so those will be planets that will be habitable. And so Kepler will be able to find habitable planets. That is the main piece of information that Kepler will yield to take us on our next step. Now, we have the next animation. However, when Kepler finds these planets, they will not be in the solar neighborhood. Kepler will be staring towards two constellations, Cygnus and Lyra, as Bill showed in his talk. And so we'll be finding perhaps hundreds of Earths, at least several dozen probably, along a spiral arm, similar to our own spiral arm. And more or less, there'll be planets which tend to be several thousand light years away from us. They're not going to be very close by. So they'll be interesting in their own right, but in the end, we're going to want to find the closest Earths, because the ones that are just a few light years away are the ones that we'll be able to follow up on the best and learn the most about. But Kepler will determine the frequency of Earths off towards constellations Cygnus and Lyra and tell us the frequency of them, and we are going to assume, because it's going to be a good argument, that that frequency is going to be the same as the frequency of Earths in our solar neighborhood. There's no reason to think that spiral arm is much different there than what it is close to us. So Kepler gives us a very important data point that will be useful for taking the next steps and trying to plan for the next generation of space telescopes. Once we know how frequently Earths are, and more importantly, simply that they are there, the sanity test will be proven. Kepler will prove that there really are other habitable worlds out there. We'll be enabled and emboldened, I think, to go ahead and take the next steps. NASA's been planning for such space telescopes for some time. There are several ways of going about the next steps. Those steps are being debated right now in various venues. One could imagine, for example, trying to find closest Earths by indirect methods, much like Kepler is doing, where you do not look for transit, but you look for the wobble of the star, as the so-called astrometric method, which also gives you as a byproduct the mass of the planet. You could also look directly by trying to take an image of a close-by star and either at optical wavelengths using a coronagraph or at infrared wavelengths using an interferometer, try to actually separate out the light of the planet from that of the star in sort of a single pixel image. And that would give us something even more important, which is hints of what the atmosphere is like. Sort of like we're learning about the atmosphere of HAT P7b, as Sarah talked about, we'll also be able to learn about the atmospheres of Earth-like planets and perhaps see if they're inhabited or not. Can I have a last animation, please? So what you're seeing here is a view of the night sky looking towards the constellation Orion. You'll see the stars revolve as if you'd spent a couple of hours out at night staring at the sky. And the hope is that when Kepler proves to us that Earths are common, they exist, the NASA and the European Space Agency and other human-oriented agencies will take the next steps and figure out how to build that next generation of space telescopes that will actually go out and find the Earths around the nearest stars. So the grand dream is that sometime, in the not too distant future, we'll be able to stand outside with our children and grandchildren and point up and say, hey, kids, look up there. See that star? That one there we know has an Earth. And yeah, that one over there, that one has an Earth too. And in fact, that one, we know that Earth has oxygen and ozone and methane. It probably has some sort of life form on it. That's what we hope to be able to achieve. It's kind of a heady vision, but it's something that is achievable in large part because of what Kepler is going to be doing for us. And for that, we have Bill Barucki and the Kepler team and NASA to thank for it. But the bottom line is, the real headline for this whole press conference is, Kepler works. The discovery of the